Hello, everybody. Thank you for being here. Welcome to the last keynote talk of the conference. It is my great pleasure to welcome Peter Bossaerts, who is the Leverhulme International Professor of Neuroeconomics at Cambridge University. And you know, this is an interdisciplinary conference, and who better than Peter to be here? Because I really don't know what to call him and what label to put on him. He is a professor of finance, or has been a professor of finance, has also been a professor of neuroeconomics, and nowadays I have met people who are firmly convinced that he's a computer scientist. And all that is okay. So he has worked in asset pricing, he has worked in experimental finance, not only worked, he has shaped experimental finance as founding member and president of the Society for Experimental Finance, I'm saying that right? And a decision neuroscientist. And his contributions in this field have really shaped research. And he has challenged conventional assumptions on how people learn, how beliefs are formed, and how people behaved, and taken together the neuronal foundations and how people react to very important external factors, not only risk, as we are used to think in this conference and others, but also complexity. And in the more recent part of his career, he has especially been bringing the study of complexity into decision-making and into decision research, and I believe that that's something that also has to happen in economic psychology. So Peter has asked me that the rules for this talk should be the neuroscience rules, which means that, of course, clarifying questions are allowed as we go, but please keep any longer questions, and I'm looking at you economists towards the end of the conference because there will be plenty of time for that. And with that, Peter, the floor is yours. We're here to listen to you and not me. Thank you very much for being here.
Thank you, Carlos, for generous introduction. Today's lecture is going to be very difficult. So I warn you, this is theoretical computer science. This is not your machine learning, your AI, your Silicon Valley, Elon Musk type of stuff. This is hardcore computer science. I started doing this work 20 years ago with a former student of mine at the time at Caltech, Deborah Meloso. We were just interested in how people actually deal with really complicated situations. In theoretical computer science, starting with Alonzo Church and Alan Turing, people quickly came to the conclusion that actually there are problems out there that are infeasible or intractable, that we really can't solve. We don't have the computational power out there. And by the way, AI is not going to solve that problem. And quantum computing is not going to solve that problem either. I'm going to actually talk about these types of problems today. And surprisingly, a lot of what you do in everyday life is exactly solving these problems. For me, this was kind of a shock because I grew up, yes, I used to be a finance professor. I grew up in stochastics, in mathematical finance, in probability theory, and so on. And then you move into computer science and solving computational complexity. And yeah, while they do talk about probabilities once in a while, it's actually not exactly how the thing works. And that's one of the things that actually you have to take into account when you're going to listen to me today. The way you have to see this is as follows. If you are gambling, you play roulette, or you play the stock market or whatever, some random device. You draw balls from an urn, typical paradigm in psychology, economics, or in neuroscience about uncertainty. You can use probability theory to predict what people are going to do. How do people act if they have to choose? They act as if they understand probability theory very well. When they have to explore, they explore randomly. Just like machines explore randomly. Right? It doesn't matter whether you follow a particular strategy to explore, randomness is extremely important here. This is not going to be the case with the problems that I'm talking about today. And indeed, a nice way to look at it is if you look at a jigsaw puzzle. Do you know anybody actually who solves this puzzle by randomly throwing the pieces on the table and trying over and over again until it fits. But you're laughing, but this is how machine learning works. And it works. It's just unbelievably inefficient, and that's why these guys out there are building nuclear power plants in order to be able to continue doing this. Humans, as you'll see, they actually think, whatever that means. I don't know. I'm not a psychologist, so these terms for me are not very well defined. But I hope today you're going to walk away with some ideas that there is something like thinking that isn't captured by our classical models, which are based on probability theory, expected utility, etc. Right? Some of our work was recently replicated in non-human primates. Monkeys as well actually think when they have to solve problems like the ones that I'm going to talk about. So that's pretty much the introduction as to what we have been doing for the last 20 years. I should also mention there are two students here from Melbourne in the audience. Hassan is actually joined, working on this paper as well that I'm going to present today, and Michelle Lee. They're dedicating their career to this type of issues as well. All right, so without further ado, let me just continue. The specific lecture today is about how do humans choose when valuation is computationally complex. We need a model of how they choose. And so first, computational complexity means intuitively that it's very hard to find a solution. But for the computer scientists, they call this infeasible problems. And you'll see later on why they call this infeasible. They are not really literally infeasible, but in many, as you make them bigger and bigger, it's just impossible to find solutions. I'm going to talk about a very particular computational complex problem, which is the 0-1 knapsack problem. And the reason why we started with that 20 years ago was because this is the core of economics. This is the budget problem. You have a bunch of items. You have a knapsack, and not all the items fit the knapsack. You have to choose. And you want to choose in a way that maximizes whatever is in going into the knapsack. If you go to a supermarket with, a €50 note, that's what you're doing, right? The question is, how do you do this? And how do you model choice there? There is no uncertainty here whatsoever, right? We're not drawing balls, randomly. It's not that you walk into a supermarket and you have an item, a Coke that may not be a Coke or something like that with a certain probability. It's a Coke, period. All right, so Gilboa, actually they proved that the 0-1 knapsack problem is one of these computational complex problems. The proof is not that difficult, but it's at the heart of economics. As you'll see, so 20 years ago, Deborah, my student, picked something out of the computational complexity literature which turned out to be extremely successful in predicting what people are doing, their effort, their performance, etc. And so we built a theory of choice based on that. But then it turns out that led to paradoxes, and I'm going to talk about these paradoxes. And then we actually had to do more. As an economist, I've become very lazy, right? First thing, you never ask questions to people. Second, you only look at choices, right? And then you come up with an as-if model that, predicts future choice. And then you get, as an economist, into paradoxes, things that don't work. You get, prospect theory and all that stuff. And what you then do is you throw more stuff in the utility functions, right? Until the thing fits. But you're going to see there's a paradox here that we can't get rid of by throwing more into the utility function. And then we had to go back to actually looking what people were doing. Unfortunately, we had the data. So we started doing what Herbert Simon, a very long time ago, said what you should be doing to explain an agent's behavior in the face of complexity. And he mentions complexity. The term complexity in 1959 was not very well understood. The math that I'm talking about wasn't developed until the 1970s, right? But anyway, so he talks about complexity. The theory must describe his behavior as something more than a featureless adaptive organism. The featureless adaptive organism is this machine learning organism, this temporal difference learning organism. It adapts using, randomly trying out. It's like a rat or a mouse in a maze. And he says you actually have to understand what the processes are that are behind it. So it must incorporate at least some description of the processes and mechanisms through which the adaptation takes place. So we started looking at what exactly are they doing. And then using computer science, theoretical computer science, in order to understand what's happening and then come up with much better predictions and getting rid of these paradoxes that we observe. So indeed, we start with a traditional as-if approach, but discover two paradoxes, which we only managed to explain when going deeper into the processes underlying choices. So that's what I'm going to talk about. There is a link here with this recent branch of behavioral economics called Cognitive Foundations of Decision Making, where Carlos is one of the contributors to this literature. And that's based on a part of cognitive neuroscience called efficient neural coding. So there are two branches there. There is noisy choice features. There are some references there. There happen to be 3 former students of mine involved in it, but I'm not responsible for what they're doing there, right? Or efficient neural coding of potential alternatives. If you have 10 alternatives, your brain has to, to be able to squeeze that into what it neuronally can actually manage to compare, right? So, and especially Paul Glimcher and his former postdoc Agnieszka Timola worked in that branch. This approach also takes into account the processes and mechanisms through which the choice takes place. So that's what really these cognitive foundations are. That's what that branch of behavioral economics is about. It's a bit related to numeracy that Alan Peters was talking about. Right? So the first part especially, you see some number, you have no idea what's there, your brain has to process this, and it's done in a noisy way, and it leads to cognitive biases because it's not perfect. Right? And then Glimcher and Timola would just say, you have 10 different choices, you can't do everything. So you're going to present that in a noisy way. The big difference between the standard cognitive foundations literature and what we're going to do is that we are not going to use flexible priors. That is, we are not going to actually take this as yet another as-if theory. Right? So in the literature, they use flexible priors that best fit the choices, but we're going to actually use the actual features of the problem instances at hand. As a computer scientist would say, this is a difficult one, this is easy, etc., etc. Right? And that's consistent with actually computational neuroscience that has inspired cognitive foundations of decision making. And there's this beautiful paper in PLOS Computational Biology by Blanco Malerba and people like Rava da Silveira that really explain that very, very, very nicely. All right, so that's introduction. By the way, I'm a neuroeconomist, right? So that's why I care about neuroscience. This talk, so I'm going to start about it to explain to you what the 0-1 knapsack problem is, and then talk about theoretical properties. This is going to be extremely hard, so clarifying questions are allowed. This is a very obscure part of math. Then we'll look at observed choices. So we collected some choices from old experiments we were running. We actually have a big database of lots of decisions made in the knapsack problem and other problems, a traveling salesperson problem, all these so-called NP-hard problems. And then I'll talk about the paradoxes, and then I'm going to resolve the paradoxes in the traditional way, which is throw more in the utility function. But then that doesn't work, and so we need Herbert-Simon's way. And I'm going to go only one way today, which is to look actually how their choice process works. How they get to, okay, this is, I think, the value of this knapsack. I'm not going to talk about neuroscience today. We also drugged people with things like Ritalin and all that stuff. It's very interesting to see what happens. If you're a student here and you're considering for the final exams this month to take Ritalin, please come and see me. I will not get to these optional more questions, so I'll skip that and I'll summarize. So what's the 0-1 knapsack problem? So this is the math of it. So you're facing an optimization problem. So you can clearly see this is economics, right? We optimize, right? You want to find a subset of items that fit a knapsack with a certain capacity. That's your budget. PI is the weight. Each of them weighs something for your knapsack, or there is a price if you have a budget. And then there's some value to it. The value of the total knapsack is just linear to start with. I can tell you when you go to quadratic stuff, as we are doing right now when you're looking at food choices with people at Oxford, then it becomes quadratic, and then, it gets even more complicated. But let's not talk about that. It's very simple linear. N is the number of items, and it's going to be really important. How many items do you have? And what are the input data for this problem? It's the capacity of the knapsack, the costs of all the items, or the weights, the values of all these items. They constitute the input data, which we will denote with some vector z, right? So that's the mathematical representation of it. This is the interface that we have been using, already 20 years. So the way, let me explain this. On the right-hand side, you have a bunch of items under out. So for instance, you have an item with 9 euros, 13 kilograms here. You have another item which is 2 euros and 3 kilograms, and we use color coding to make it easy for people to see what the value is, and then the size tells you what the weight is. And you're supposed to actually try to figure out whether you can find a subset that you can put in the knapsack. And you'll see there is a weight limit of 14 kilograms, and at this moment with these items in the knapsack, the value is 22 euros. And the nice thing is people just move things in and out so we can see what they're thinking, hopefully, right? So we see more than just the end result. So that's the knapsack. Everybody gets this? I mean, it's very simple, right? We've also studied other problems like traveling salesperson problem. I'm going to say something at 3 sat later. This is your mathematician's daily job. Proving whether theorems are right or not, right? That's 3 sat, and that's the core problem that I'm going to talk about. So I'm talking about really difficult stuff here. And weighted cost shortest path problem, which I call the Google problem. When you ask Google to go from here to Valencia, how do you go, right? And sometimes it doesn't do a good job. All right, so first, an algorithm. How do you solve this? Right? Of course, you can randomly try. You throw in items as you want. And I'll just show you that this is going to be our benchmark. What if people actually randomly threw in as many items as they did and then replace, right? What's their performance, right? I'm going to compare that to simple algorithms. And the greedy algorithm is probably the simplest you can think about, right? Which is you rank the items by decreasing value over weight, or value over price, that is, by decreasing bang for your buck, as the Americans would say. You fill it till capacity, and you skip the items that do not fit. All right? Great algorithm. This algorithm, if you could chop up the last item, will give you actually the optimum. Right? So if you're in a world with perfect divisibilities, this gives you the optimum. In my world of the knapsack problems, we can't chop up the last one. The greedy algorithm can be arbitrarily bad. That is, give me an epsilon, very small number, as a fraction of the optimal value. I can find an instance where you can actually not even reach epsilon. Right? I'll come back to that later. So this is also tells you that you're in a very different world. What you learn about calculus is useless here, right? The greedy algorithm does not guarantee any level of economic performance. That's what I just said. And economic performance is value attained relative to the optimal value. Yet the greedy algorithm, without skipping, provides the optimal solution if items had been perfectly divisible. Just repeating what I just said. Some definitions. The input size is called the absolute value of C. Literally what it has to be, this is actually really important when you do this work exactly, when you do experiments. You will notice that humans respond to input sizes the way the computer scientists care about this. We got into a fight with referees from the IAREP who thought we were tricking things. No, we were actually following computer science, right? So it is the length of the binary representation of Z which is bounded by a number proportional to n in the case of the knapsack problem, but not in the case of the traveling salesperson problem, etc. So it's a bit difficult. So the version I just showed you is the optimization problem, but the theory is not based on optimization problems. There is something about optimization problems as well. You'll see that later when I talk about approximation complexity. But the basic theory that was developed in the 70s is based on another problem, which is the decision problem. And what's the decision problem is basically, can you reach a certain target, right? Can you build the knapsack up to a value of 40? Yes or no, right? If yes, tell me. How? If no, that's difficult, right? And this is where the asymmetry in these problems are going to be. It's very hard to convince somebody that there is no solution. It's easy to convince somebody that the answer is yes, you can reach it. You just have to give an example, and the person can then check, right? So this is basically mathematics. Given a target, I'm going to call that epsilon. That's Greek capital epsilon. Given that you have a target, can you reach this with this in this particular setting, this particular instance of the knapsack problem? Right? First, you have computational performance. What is computational performance is how hard it is to correctly solve an instance. Right? So I'm really focusing on correctly. You're not allowed to guess here. This is one of the features of this part of mathematics. If you tell me yes, it really has to be correct, right? So the knapsack problem is a combinatorial problem, right? Because it has to do with combinations. You know, a lot of people think that intellectual discovery or art is exactly that. And in fact, there's a lot of evidence from looking at records in patent offices that this is exactly what happens. That the vast majority, 99% of patents are really combinatorics. You're recombining things, or you're putting new combinations in place that nobody actually had thought about. Right? This is actually how we started thinking about this problem. So it's a combinatorial problem, and you can clearly see n, if n is large. So let's say we're going to talk about n equals 10 or 12. So there are 2 to the 10 possible outcomes. Now, if you go to a typical supermarket, they usually have about 40,000 unique items. So we're talking about 2 to the 40,000, right? Which is a big number. Now, we can also go to Aldi, or for Europeans here, Aldi or Lidl, right? Because they only have 10,000 unique items. But it's still 2 to the 10,000, you know, and even the Germans can't figure out what to do, right? So that's the problem here, but that in itself doesn't make it really difficult. It is a little bit more than that. So the decision version of KP, that's the version where I ask you, can you reach a certain level, yes or no? And if yes, tell me what the witness is. So the first thing you have to say this is in the class NP. I'll tell you what NP means later. Right? Namely, it's easy, as I already mentioned, it's easy to verify a solution. That if I say, yes, you can reach it, I can show that to you by telling you here are the items that you can put in there and just count it. So it's very simple for you to figure out that I'm right. However, when I say, no, you can't reach this, how am I going to convince you without going through the 2 to the nth possible cases? Right? So this has to do with co-NP and all that stuff. So you can see this asymmetry is the core of computational complexity, this branch of computer science. Right? When there does not exist a solution, we call that it's not solvable. So I'm going to use that terminology. It's also in the class NP complete. What does that mean? That's where the math comes in. NP completeness, if you remember your math classes, it has to do with the closedness of a set. You can go from one element to another element and without getting out of the set. The way you have to see this here, you start from the job of a math guy, which is to prove theorems that they're right, or to disprove theorems, right? This is the 3-set problem. It's a problem in Boolean algebra, right? Can you actually find values, Boolean values, zeros and ones, that make a particular logical statement correct, Boolean statement correct? It's a very, very hard problem. And what happens is you can actually reduce an instance of that problem into a knapsack problem. And you can reduce that in very simple terms. It doesn't take much time for you to do that. That is, as the size of this three-set problem increases, your translation doesn't increase more in terms of steps than a polynomial in the size, right? So that's easy. Anything that's polynomial is fantastic because computers can do that, right? So easy means the number of computations needed increases at most as a polynomial in the size of Z, of the instance. So the class NP complete is very nice because you have all these problems: traveling salesperson problem, knapsack problem, the craft coloring problem. There are about 150 problems which you encounter any day. Even little kids, 3 years old, when they have to color a little map, and they're not allowed to use the same color for adjacent parts of the map, right? That is a very, very hard problem. You make sure that when you have an infant of 3 years old, you start training it on it, because it will be very useful for the rest of life. All right, so we have tested all of them, but as I said today, I'm going to talk about the knapsack problem because some of you are economists and you like to spend money. The optimization version of KP is called NP-hard. I promise we're going to say what NP is. NP is non-deterministic polynomial. That's something that Alan Turing, and the local hero in Cambridge, invented to actually describe the beginning of this type of infeasible problems. Right? It's not important that you understand where that comes from. It's actually important for the math. He also developed the first abstract version of a computer. And of course, he was thinking about electronic computers. But one of the things that we have been able to do is to show that biological computers, like the way we do, that actually they satisfy the same laws. And this was a conjecture that Alonzo Church and Alan Turing had before the Second World War, that actually the rules that we're talking about, that the math, that his Alan Turing's machine, the Turing machine as it's called, is a universal representation of computation, including biological computation, despite the fact that our brain does not work like your computer. All right, so the optimization version is NP-hard. Verifying whether one has reached the optimum requires solving an NP-complete problem. That's basically the best way to define this. This is very different to your standard calculus problems. If you're on top of a mountain, how do you know that you're on top of a mountain? You look in all directions. When it goes down, you say, okay, so at least I've reached a local optimum. That is not true for these problems. You can easily trick people into believing that when they look around, oh, well, I'm at an optimum. You're actually not at an optimum, right? So, and I'm going to exploit this. The fact that when you actually stop searching as a human, you have no clue whether you've reached the optimum. There is no cheap way for you to test, okay, I shouldn't search anymore, right? So you don't even know whether you're on a local optimum, right? So that's going to be very important. Okay, so now second part, approximation complexity. What's approximation complexity? So, economists are not necessarily interested in whether you find a solution, but how good the solution is, right? When you do an exam, it's not that actually you're mostly interested in I find the right answer, but, can I get partial marks? That is, I get as high marks as possible. And so that's approximation complexity. First, I have to say something about an algorithm. What's an algorithm? It's a number of steps that you're going to take in order to solve this optimization problem. But it has to terminate in finite time. Finite can be very, very large. Right? It doesn't matter. But it has to terminate in finite time. And then it has to suggest a solution. Right? So I like to think of it as a heuristic, but I get into fights with psychologists about this. So I'm not, since there's some distinguished psychologists here, I will not use that terminology. What's the value that an algorithm can reach on a certain instance Z? That's a V of A of Z. That's the value it can reach, right? If you use that algorithm, and it may not be the optimum. And the ratio of the value you can reach with an algorithm for a particular instance Z over the optimal value is the performance, the economic performance. That's what most economists would care about, are you 50% towards the optimum or 20% or something like that? That's what they care most about. Now, more definitions. An algorithm is an R approximate algorithm when it guarantees that you can at least get R being a fraction. Let's say 50%. I told you the greedy algorithm, R is 0, right? It guarantees 0 performance. So don't use it, right? Paul Milgram is a good friend of mine, so for those economists who know him, so I can already announce that, when he did the FCC spectrum auctions and he needed to clear the markets, which is an NP-hard problem like this, that he used the greedy algorithm, right? Nevertheless, the US government made $20 billion. So it can be good, but not always. So that's an approximate algorithm. And then you have a subset of these NP-hard problems, which are polynomial time approximable. So the greedy algorithm is very simple, right? You just have to sort everything. Sorting is something you can do very efficiently nowadays. It's a polynomial time algorithm. The time you need increases as the logarithm of the number of items you have to sort, right? So the greedy algorithm is a polynomial time algorithm that reaches a 0%, a little r equal to 0%. I'm going to show you a family of algorithms where you can actually increase that to 50%, then 2/3, 3/4, 4/5, etc. And then with that, actually I'll be able to show that the knapsack problem is in p-TAS, which is this collection of problems that are polynomial time approximable. There are problems that are not polynomial time approximable, for instance, a traveling salesperson problem where you have to go through all kinds of cities in the shortest way when they violate Euclidean geometry, right? That is when there's congestion. So some of the hardest things you have to do in life is to drive, right? Because they are non-approximal TSP problems. So stay home. So here is the family, an example of a family of approximation algorithms that you can prove to that KP is in p-TAS. So this is the Sani-K family. This goes back to Sani, a computer scientist who developed this in 1975, right after the discovery of these the set of NP-complete problems. And then Debrayman also revived this when he was trying to study how humans did this. Were solving knapsack problems. So what it is it's a family. So K is going to be a number. When K is 0, you basically, that's the greedy algorithm. Right? So basically what you do is you sort all the items and you take the top until you can find the solution. You skip items that don't fit until you can do no more. Case 1 is you start filling the knapsack with a randomly chosen item and then you apply the greedy algorithm. And you try it all singletons, all choices of a single item, and then you apply the greedy algorithm. Right? So that's K equals 1. Requires more. You have to sort n times, right? Because n times you have to put an item in there already. Case 2 is you start filling the knapsack with a randomly chosen pair of items. Now you have to look at all the possible pairs and then apply the greedy algorithm, the sorting algorithm, and you repeat for all possible choice of pairs, and you pick the choice that generates the maximum value. Even more effort is required for K equals 3. You start filling the knapsack with a randomly chosen triplet of items, etc., etc., etc. You can see how this goes, right? The problems that we are going to, I'll say this in a minute, but you see the idea, right? Now, note that the number of computations needed increases in K. This is going to be very important to understand humans, we thought. The Sani-K family can be used to show that KP is in p-TAS, right? And the reason is the performance, the economic performance that's guaranteed when you take out of this family, the algorithm with level K is K over K plus 1. So if K is 0, that is a greedy algorithm, you guarantee 0. If K is 1, you guaranteed 1/2 of the optimum. If K is 2, you guarantee 2/3 of the maximum. When it's 3, 3/4. Right? You can see this, and you can increase this. Each of these algorithms is still polynomial time. right? Because it only requires sorting, which we know how to do very efficiently, right? All right, so theorem that basically says what I just said. It's in p-TAS, right? Now, you can get from that a measure of difficulty, and this is where Deborah Melosso comes in. She said, okay, well, we can turn things around, right? So a difficulty of an instance of the knapsack problem equals k star. So when there's a star, it's about an instance. When its solution can be guaranteed with an algorithm where you pick k equals at least k star, right? Because then you're guaranteed to find the optimal solution, right? Important for the rest of this talk, k star cannot be determined beforehand because you need to know the solution before you can prove which of the family of Sani K algorithms can find you the solution, right? And one of the perplexing things, to already tell you what we found, one of the perplexing things that we found is that it is as if people know what k star is before they start. Not only that, in a market setting, this is where Hassan and Ravi comes in. We know we run markets with these problems. Markets actually within 30 seconds tell you what k star is. But the market hasn't figured out yet what the solution is. Wait a minute, there's a problem here, right? So the effect of that is that if a computer, and I'm talking about a human computer as well. Computers used to be humans, by the way. There's a beautiful movie made of the computers that NASA used, to send rockets out there, right? There were 3 black ladies who were doing all the computations. Later on, we now have electronic computers, right? If a computer is to be able to solve correctly instances of difficulty up to k star, then it should use Sani K equals 2 k star, right? Beyond k, when k star goes beyond k, then your performance is only k over k star over k star plus 1. Now, let's talk about resource rationality, right? So resource rationality is a very economic concept, but the main reference is Leader and Griffiths, comes out of computational neuroscience. You would expect that biological organisms are resource rational. They're going to use resources in a way that economists will like. That is, it's more difficult. You're allowed to use a little bit more resources, but don't be too stupid about this, right? So a resource rational agent trades off economic performance against difficulty. That's what you expect, right? This is related to an axiom that is in Andy Kaplan and Mark Dean's article in the AER applied to rational inattention, right? So it's an axiom, right? Rational agents should trade off performance against economic performance against difficulty. So a resource rational agent's economic performance will, as a result, decrease in k star, right? The minimal economic performance also decreases in k star. So the minimal across all possible instances. As you match that with k star, you should see a decrease. I'll show you some data that will become much more intuitive, right? As things become more difficult, that is, as k star goes up, you are allowed to spend more effort, but your economic performance would go down. Imagine that you give a math exam or something similar, an economics exam, and the students do better on the difficult questions than on the easy questions. You're going to say, this is crazy, right? I was told that actually Chinese students are educated with this motto that first solve the difficult ones and then the easy ones, right? Which is for an economist, no, don't do that. First solve the easy ones, right? And then the difficult ones. And then you're going to go down in performance. You get 7 out of 10 on the difficult ones, but 10 out of 10 on the easy ones. Skiers should never fall on a green slope, unlike me, right? If you fall on a double black diamond, that's fine, right? And you're going to see that's going to be violent. I can prove all this stuff, but we're not talking about proofs here. So we're going to look at choices. This is data from a bunch of experiments, and one actually that was not published yet. We have all these data. So 2,907 choices on only 8 carefully selected instances, and you'll later on see that they were really carefully selected. I must commend Deborah on being very far-sighted. Of course, you will say, I didn't know that, but you'll see that later. 10 or 12 items, and you think, oh, well, that's, 2 to 10 items. It's not that much, right? Sets, it's not that much. Payment is based on economic performance. We're economists, we do that. The instances selected, she selected instances initially, and this is the first paper that it's not mentioned here, that's the Melosso paper, to spread K star. So we had K star equal to 0, where the greedy algorithm can find the solution, 1, 2, 3, up to 4. K star is 4 means that you have to put in 4 items already before you can use the greedy algorithm to find the solution. That is very challenging. Right? And at the same time, we should not see any effects on performance if they randomly tried things. If they followed the finance professor's advice that just randomly try out things. If you want to invest in the stock market, just throw darts at the Wall Street Journal. Right? So here is, I hope you can see this because the confidence interval is very, very low. On the x-axis is the difficulty of the instance at hand. So 0 means the greedy algorithm can find the solution. 4 means you need to put in 4 items before the greedy algorithm can find the solution. On the y-axis is the computational performance, that is the chance, the proportion of outcomes, of our almost 3,000 outcomes, where the correct solution is found. And you can see it goes down, right? The significance is very high. You see all the, you can do fancy statistics with this, but I think you should be convinced that it goes down, right? And this replicates extremely well. The economic performance, however, increases with the difficulty. Right? So what happens here is, this is just the average. The simple average, this is the average of the individuals, and then you can do some fancy linear regression with participant random effects, and then you'll see that actually the effect of K star is positive. As we give them more difficult instances, they actually end up reaching a higher performance. They do very good on the difficult math questions compared to the easy one. Of course, they don't know because they don't know what K star is, right? These instances are so difficult. In the experiments here, we have 8 instances they have to solve, but they have to solve them twice. So we have these guys who solved it upon the first attempt, but then 30 minutes later, we ask them to solve the same instance and they can't find the solution. That's what we are talking about. The other thing you can show is that participants choose as if they're indeed picking a member of the sine K family. So when instance 4, for instance, in one of our experiments, instance 4 has sine K equals 0, which means the greedy algorithm can find it. What do you see here? This is basically a density of, on the x-axis, their moves. The first move, the second, the third, up to the 11th move. And here are the items. They're ranked from the highest value over weight, or value over price, to the lowest one. As you can see, the first several moves here are on top. Most of the density is here on top, which means they're most likely to actually pick high value over weight items. They're applying the greedy algorithm. K star is 0, which means that they should apply, if they really want to be efficient, the greedy algorithm. Instance 7, K star is 4. And as you can see, they don't even look at the highest value over weight item. There is here a blob there, but that's the 4th item in the row. So it's as if, they look at instance 7 and say, this is, it's very clear, K star is big. How can they know this? They haven't solved it yet, right? But they do behave as if this is true, and as economists, that's all we need, right? Why they do this? Magically, right? I will not quote economists at this moment. All right, so it's also consistent with the fact that the effort increases in K star. That is, it looks like they spend more effort. I mentioned that the greedy algorithm, right, doesn't require much effort. You sort, you fill to capacity, end of story. When K is 4, you have to try all quadruples of the items, and then the greedy algorithm. There is lots of 4 items that you can get out of 10, right? It's all 10 items in combinations of 4, right? And you can see that the effort, if you look at the time in seconds that they spend on this is in seconds, right? So they start with when sine K is 0 with 140 seconds, and they go up to 180 seconds, right? So that's consistent with this as-if story. It is actually as if you look at the choices and their effort, our theory is correct. It's also consistent with the minimal economic performance. It increases with K star. It's not only that they do best on the difficult questions, the minimum performance is highest there, right? So on the y-axis, the vertical axis, the minimal economic performance. So the paradoxes, you can guess now, right? First is resource rationality is violated. Resource rational agents' economic performance ought to decrease with K star. And their minimum economic performance, that is the fraction they get as a function of the maximum, it ought to decrease in K star, and it doesn't happen. Then the second paradox is, how can they pick the right K if they don't know what K star is until they've solved it? And as I claim is they never know what the solution is, because figuring out whether you actually found the solution means solving an NP-complete problem. All right, so that's where we are at. And I just want to make sure that I'm on track to deliver here. Okay, so now it's going to be still a little bit of computer science. So we're going to do this the traditional way first. Maybe we did not measure complexity correctly. And so the economists, what they do is, well, just throw in some stuff. So in finance, for instance, the initial model was people are averse to variance. Maybe not, you know, and they found that people actually are. They like positive skewness. So they throw that in their model, and it works better. We did the same thing. We actually look at how computer scientists would measure instance complexity. So the third author on this paper is Nitin Yadav. He's also from Melbourne, and he's a computer scientist. And he wasn't particularly fond of this sine K thing. He said, you know what, we have these solvers, and they have their own way of measuring how much time you need, how complicated the problem is, and which is called propagations. Right? And what is propagations? Basically, when an algorithm that finds the solution goes through finding the solution, it looks at first at the feasible set and what you can actually kick out elements, items that are dominated. Or when you say, okay, I want this item to be in, then you know certain other items cannot be in there anymore. Right? I checked yesterday, this is the reason that ChatGPT also uses, by the way. But I was still not convinced that it was reasoning on its own. So propagations is a measure of difficulty. The more propagations, the more of these weeding out that it needs to do to find the solution means that actually it's more difficult. And sure enough, you can see that the computational performance increases not only with, or decreases not only with K star, which I already showed you, but also with the number of propagations. The number of propagations, you see this is an order of magnitude, 2 orders of magnitude larger than K star, which is between 0 and 4. However, it doesn't solve our paradox. Economic performance continues to increase. I already showed you increases in K star, but it also increases in number of propagations. Here are some, if you like small p-values, well, you get them, right? Now, just terminology, sine K and propagations, they measure algorithmic properties of an instance, and I'm going to switch to other properties soon, because algorithmic properties depend on algorithms, the sine K family of algorithms, or G-code in Minizinc, which is what the computer scientists love to work with, because it's an all-purpose optimization or solver, right? Now we're going to do this the Herbert Simon's way. We're going to actually look at what people actually do. So we're going to go back to a paper we published exactly 10 years ago. And one of the things we noticed there is that if you look at the step of the sequence, when people are trying to find the optimum, you'll see that initially the gain in economic performance is very high, but then it drops to 0. And pretty much for the rest of time, from step 10 up to step 80, not much happens. They take an item out. If they take an item out, they, of course, lose economic performance. When they put one in, it goes back up, out, in. So they basically do depth first, right? You can say a few other things about this, which are related to depth first. That is, they first fill the knapsack to capacity, and then they start messing around with marginally. Those who mess around more than marginally do better. That's the first point there. And then the second point is that you can predict the steps needed. You can actually do a lot of prediction here just based on the data that we have, which suggests to us that what they do is they fill the first knapsack, and then they're trying to solve a sequence of decision problems. Can I get better? Can I get better? Can I get better? Right? So that's what's called depth first. Under depth first, one views the optimization problem as a sequence of decision problems where the target value is gradually increased. So mathematically what it is, in each iteration, you say, okay, so I've just filled this. Can I improve? That's an NP complete problem. Yes, okay, I improve. Should I continue, right? So every time you actually try to improve. So you solve the decision problems where you actually increase the target, and then at one point you stop. The question is, where do you stop? Right? To obtain an approximately optimal solution, you cut the sequence short at some tau because you're not going to go all the way to the end. This may actually require too much. So tau is the stopping time of this process of solving decision problems. How to set tau? For that, I have to digress to another part of computer science. I told you it's going to be difficult, right? So this is work we actually had to do as part of this because this was not known. It was known for other problems that there was something like a phase transition or so. So let me just explain what it is. We need two metrics. You take an instance. The instance consists of capacity, weights, or prices, and values. With that, you construct normalized capacity. So it's C divided by the sum of all the prices. So if you have prices are very high and your C is very low, you have a very constrained set. Elon Musk sees infinity, the sum of prices of all goods he can buy is finite. So he has an unconstrained problem. Normalized profit is epsilon, that is the target I'm going to reach relative to the sum of the values. Right? Going back to Elon Musk, he wants to go to outer space, to Mars, whatever he wants, which is epsilon is very high, but the sum of the values can't even reach it. Right? So that's basically also an unattainable target. Then what you do is you put on the x-axis the normalized capacity of all kinds of instances. You can randomly draw this instance. You can actually, sometimes what we do is we actually compute the normalized capacity of all the instances that you can imagine and the normalized profit of all the instances. So profit is vertical, cost is here. So if the normalized cost is way there, it means that actually you don't have much budget constraint. If the normalized profit is very, very high, that means that you're trying to go for the sky, you will never reach it. And the way that actually you can see this is green means the probability that you'll find an instance there, or the fraction of instances there that have a solution. Yes, you can reach that level, you can solve that problem, is 100%. Red means 0. And then you have this region in between which looks like a phase transition. It's convex, we proved why it's convex and all that stuff. That's where the hard problems are. They're actually slightly below that, right? So what happens when you're trying to solve an optimization problem? Of course, the normalized capacity is given. So you start at a point here. The normalized profit, you don't know what the maximum is. So you start, let's say, at 0. And then you work yourself up vertically here. And initially, this is very easy because pretty much every instance there is solvable. So it goes very, very fast until you reach that boundary, that phase transition. And then people start choking. And choking means I'm going to stop. And I'm going to show you this is exactly what people do. All right? So there is a proposition about these features that exist, a region where the instances change from all solvable to all unsolvable with a convex upper bound. And the average invariance of number of computations is the highest regardless of solution algorithms. So we tried 2 major solution algorithms. So that really predicts very well what's happening. We published this in Computer Science. So now how do you determine tau? So we now have a behavioral hypothesis. The human stops search at a profit value where the decision instances are likely to be unsolvable. And the search stops even for lower profit values when the instance is over-constrained. So in other words, tau is determined by a combination of the normalized profits at the optimum value. We call it NP star, so that's the optimum of the optimization problem. As NP star increases, people stop earlier. And normalized capacity. If the normalized capacity is very large, they'll search a lot more because they say, oh, wow, this is a wonderful world. I can try all kinds of things. And so the idea would then be that actually if you take the ratio, tau would decrease. You run the regression. So actually, a first terminology, sorry. NP star and NC measure structural properties. They are not dependent on an algorithm. They have to. I can see an instance and I can tell you exactly what NP is, but not NP star, but you need the optimum, and then C, right, which are properties that I can actually find beforehand, right? They do not derive from solution algorithms. So here is, the search times are not only determined by sin k and the propagations, but by NP star and NC, right? So these are mathematical properties that then allow you to predict how long do they search? I'm not using classical search theory here, right? It comes out of statistics because then I need to know what their subjective beliefs are. I have no idea what their subjective beliefs are, but I can use computer science to make predictions here. And you can see it's very successful here. Does this lead to increased economic performance when sin k star increases? So this was actually phenomenal. I told you that actually originally these instances were picked by Deborah Melosso to have a spread in k star. They are also spread out along this barrier in the NP-NC space. So let's take sin k equals 4 here. This was the most difficult instance, we thought. But notice, it actually is not constrained because NC, normalist capacity, is very high. Right? So basically a situation where the budget was very high, or the capacity of the knapsack was very high. And it's way below the phase transition, where pretty much all instances are solvable. Right? So economic performance is high. Why? Because they keep on searching. Right? So that's mechanistically explains what happens. So it's not very constrained, and NP star is below the 45-degree line. When you look at k star equals 2, I don't know whether you noticed this, there was a dip at k star equals 2 for economic performance. And the reason is, right, here is 2. Right? 2 is more constrained than 4. So the normalized capacity is there, plus it actually is closer to the phase transition vertically than 4. And people choke on it. Right? And you can go on with k star equals 3, etc. You can explain all this. Let's do just econometrics. We just do regression, and you can see economic performance now no longer depends on k star and propagations. In fact, actually, the coefficients are negative now, but they're insignificant. They used to be positive and significant. That is, the economic performance went up with k star and propagations. Now they behave with respect to NP star and NC exactly as you expect. So resource rationality is restored, right? So this is Herbert Simon. I have one of these old people who had the pleasure to have been his colleague at Carnegie Mellon University when I was a little kid. assistant professor, right, Herbert Simon is going to say, see, I told you, you actually have to look at what people are doing when they're solving this. Computational performance, interestingly, is determined solely by these algorithmic properties, not by the structural properties. Right? So as a result, we get a beautiful pattern. Computational performance depends on, Deborah Melosso's Sine K and on, Nitin Yadav's computer science measure of difficulty, but not NP star and NC. Economic performance, in contrast, depends on the P star and NC, so non-algorithmic stuff. And the time it takes depends on all four. Right? So it's a remarkable result, I find. I hope you share my enthusiasm. Remember that 20 years ago, we knew nothing, zero about this. There are more questions there, but I will run out of time if I look at these questions. I want to summarize and then come up with some conclusions that tell you, where we're actually also going with this. So first, the knapsack problem is an NP-hard combinatorial problem where computational and economic performance as well as effort can be predicted by a choice model built on the intuitive Sine K family of algorithms. Thank you, Deborah. That was a fantastic idea. Unfortunately, the model generates paradoxes, which forces us to either decide that choice is anomalous or the model is purely as if. But we can, of course, do stuff. We can throw stuff in the utility function, but that appears not to solve the problem. Right? Expanding the notion of complexity by including measures related to reductions of the set of feasible items. Propagation does not eliminate the paradoxes. This is like, you're an expected utility guy and you see some paradoxes, loss aversion and so on. What you do is you throw in a reference point. Fantastic, we solved the problem. Right? No, you didn't solve the problem. You enriched your model to fit the data. Right? Sine K and propagations measure algorithmic properties of the KP instances. And that was the weakness from the beginning, actually, especially the computational neuroscientists were really after us for having used something that wasn't consistent with the data as to how people were searching. But, I put on my economic hat and we said, I don't care about this, right? I don't care about you neuroscientists, I'm an economist. Close inspection of the path during search reveals a depth-first approach, which is the first full knapsack attained can be predicted by Sine K and propagations. And by the way, the first full knapsack really determines with a very high likelihood whether you're going to find the solution or not. And for those who take Ritalin here just for the heck of it, or dextroamphetamine, right? Adderall, whatever they call this, or modafinil to study, that actually is affected by these medications, by these drugs. You become random. And your first full knapsack is really important. Because if you start very low with your first full knapsack, you have to solve a lot of NP-complete problems. And then you can see the total performance goes down. Right? We have a paper that we published, a pharmacological paper a while ago. Right? So while the remaining sequence of moves until stopping time are predicted by structural properties of the decision problem instances encountered on the way, and as a result, the total time till choice is predicted by both algorithmic and structural properties. So that's the summary. Conclusions, first for economic theory. Suboptimality choice is not just random. The fact that actually people, when they go to the supermarket and don't do what's optimal, don't think that actually just that she can be modeled by some random turn, some logistic regression or something like that. No, it has structure, right? I have a student, a PhD student at Cambridge who's using these results that we have in order to actually model revealed preference using structural properties of the instance at hand. The type of suboptimal choice we discover, namely the Sine K family, one of the things you can show with this is that if you actually follow those algorithms, which I try to convince you are very efficient for budget problems, yeah, they have their polynomial time algorithms. At the same time, if you want to model their choice as if they're maximizing utility function, you will not find a utility function because they violate the axioms, sure thing principle, etc., that you need for that. We pointed this out a long time ago, but Kamara has a very nice paper in a computer science journal that proves this in general for the greedy algorithm. But it applies to all the sine k algorithms. And my postdoc Ioannidis is looking at to what extent does this bind, right? Because we have, of course, violations of the transitivity and so of choices. Does this really matter? The incentives cannot be based on contracts that assume agents are expected utility maximizers, right? So contract theory is based on, I'm the principal, I have a math guy, I actually had a math postdoc, and I told him to do this here. And then, I can just write down the optimal contract for this, right? And the optimal contract is usually, if it comes back and it says can be done, I shoot him. Well, presumably that's not a good idea, so I'll take a second best contract, right? It's standard contract theory. People like Lafont and Tirole and so have worked on all that stuff. This is in a probabilistic context, but we don't have a probabilistic context here. Right? Hassan, sitting there, is working on what contracts do work. For policy, the important elements are here. Search paths differ dramatically across agents, so communication is needed. And that was actually our original paper with Deborah Menosso, which published in Science, because it was rejected by AER. And so what you do when the American Economic Review rejects your papers, you go to Nature or Science, right? And then Hassan actually had a talk here yesterday. This is related to a history of patents. Very interesting. I didn't know about this. There's this Italian economic historian, Nuvolari, who contacted us and said, did you know, long story, I can talk about that if you're interested in the question and answers. The consumption problem is NP hard. I already mentioned Gilboa, Ichak Gilboa, and others show this. The question is, will markets select instances that make it easy on participants? In economics, especially in the Chicago world, there is this view that markets are wonderful. They help people with everything. If you have a problem with electricity, set up a market. If you have a problem with liver transplants, set up a market. If you have a problem with whatever, you set up a market. The question we ask ourselves is, what about the agents in the market, right? If the market needs to equilibrate, actually, will it induce difficult budget problems? And it turns out the answer is yes. In fact, to equilibrate, markets make people miserable, especially people who have basically the same preferences. So you think about the middle class, they all want to have their electric car, they all want to go, if you're in England, they all want to take a vacation in Alicante or Benidorm or something like that. They all want to do the same thing. And then, the world for the Brits is complicated. And of course, then they blame the Europeans on it, and then they do Brexit, but in fact, it's the markets that may be doing it. So we have a paper on that with experiments. And then I have a PhD student in psychology, political psychology at Cambridge, who works on the relation between complexity and recall and memory, which is very important for political systems. So he's a political psychologist. The Europeans have an incredibly complicated system with coalition governments, right? It turns out actually people know a lot more about what's going on than if you have a two-party system. Recall helps, and it has to do with actually the way you have to solve these problems. I can say something about psychology, but I don't dare to. Thank you for your attention. Yes. Who starts? Mr. Offer.
So a couple of, one comment maybe and one question. First of all, thank you very much for a very interesting talk. You warned us that it will be difficult, and I was afraid, but it was interesting nevertheless. So one comment, you mentioned the supermarkets that have 10,000 or 40,000 items. If I understood correctly, you talked about different products.
SKUs, as they call this, uniquely identifiable items.
So maybe the consumer's problem is even more difficult than what you described, because the consumer can buy 2 units of a product or 3 units. So
No, absolutely. You're right about this, right? But us poor consumers, usually not, right? That's Elon Musk's problem.
Yeah. And,
but I would buy 6 beers, not 1 beer, right? So yes, and that adds to this, right?
Yeah,
do I buy a bottle of wine and beer, or do I buy 2 beers, right? So yes.
And I wonder, you mentioned that when you say that there is no solution for attaining a certain level, yes, you cannot really prove it. And I wonder in a subset of cases if my intuition is correct. So it seems to me that if you allow indivisibilities, that will always give you better yes, value than when you have a constraint that you cannot divide goods. And then the level that you can get with indivisibility, when you can divide the goods, is easy to compute. Yes. So anything above this, you can maybe easily say that cannot be achieved. Yeah. Is that right?
Yes, that is correct. And you can also see the point of view from the producer's point of view or the seller's point of view. Just make sure that things are indivisible, right? Rather than perfectly divisible. So you want to go to the gym. I don't know, you cannot pay per minute. You have to take a 1-year subscription. Right? Which has been explained in economics in other terms, but that's really it makes computational very hard to figure out which gym should I go to. Should I take the gym, or should I use it to buy a dishwasher? Right, the same amount of money. So I see once you start thinking about the last 20 years, you go around the world and you see enormous amount of deliberate, what economists call obfuscation, but it's not really obfuscation. It's not that you get value plus epsilon, epsilon is noise. No, you actually know exactly what it is, but it's just difficult for you to figure out whether you should buy it, right? So partially, making sure that you can buy very, very little small pots of yogurt, but you have to buy the big one, is a way to make people's lives miserable.
There was an interesting point about this in Israel some time ago. The government made a law that requires the parking garages to price by the minute and not by the hour in order to benefit the consumers, but it resulted in price increases because when you price...
Because of the effect that you just mentioned, it was now easier for people to actually make an optimal decision, and they could spend more money, and that could have been the effect, right? So that was my guess, that there was more utility, and more utility means they're willing to pay more for it, right? So that, and of course, that means that these parking guys initially were stupid to bill by the hour, right?
Well, that is a different discussion, but yes, yes, thank you very much.
Yes, thank you.
I don't know whether this question has sense or not, because you propose a model without utility function. But I would like to ask whether in this space where is capacity and a profit target, is it possible to introduce the Herbert Simon idea of aspiration? Or not, or you are not interested, no. Because his definition of aspiration is based on the utility function,
It's very hard to go back. You're absolutely right. It's not that there is no utility there. There is no utility in the economics sense. That is what Tversky and Kahneman would call decision utility, right? The representation of choices. That's not here. But there is a preference that underlies everything. Each of these items has value. Now, with respect to what you said about Herbert Simon, yes, we see satisficing. Right? That's what your question. And originally, this is the paper we published 10 years ago. We interpret this effect as satisficing. Right? They increase, this is the gain in economic performance, and they gain, and then after a while they stop gaining, and at one point they basically say give up. But they give up a long time after they reach, on average, a gain. Right? And for us, initially, this is 10 years ago, we wrote all kinds of stupid things about this, right? So, and we were musing about Herbert Simon. But now we can explain that because this is people's attempts to move up in this space of normalized capacity, this space here. They're moving up. And one of the other things, so we did a lot more work. For those who want to search this in economics literature, you will not find anything. So you'll have to go to cognitive science and neuroscience and computer science. But one of the things that we found is that people spend a lot of time on instances at the upper boundary of this. So where there are few instances that have a solution, or even none, right? Which is crazy, because if I ask you for a target, can you find a knapsack that will reach this target? You can as well just say no, and I don't spend any effort. Computers spend a lot of time there too, but they are asked to find a solution. And so they're over-investing in it, right? When you ask a computer, can you please solve this particular instance, the computer can actually work for, so at one point actually our computer was going for 3 weeks to find out the solution with 50 items. And then in the end, we switched off because the computer wasn't willing to tell us how much more time it needed. Well, it cannot tell it, right? But humans also have this huge bias. In the space, in the red space, just above the phase transition, to just go after the unicorns, the unique cases, instances. Yeah, well, I know it's over-constrained, but you know what? Let me try it. Elon Musk, you know what? It's stupid to go to Mars. You know, we cannot do that. But you know what? I'm going to try and give me money, right? And humans have that huge bias. I haven't talked about this here yet, and it's not clear where this comes from. We have to do work on that. This is actually something that psychologists should definitely be interested in, because it could be related to personality, it could be related to all kinds of other features. Because purely mathematically, you shouldn't even bother to, once you're in the red zone, right, just say, you know, forget it, I'm not going to do it. Yeah, it is related. So don't forget that Herbert Simon, satisficing, he proposed this at a moment that the concept of complexity was not well defined. As I said, you know, NP-HARP, the categories of NP-complete problems, the fact that there was a link wasn't discovered until 1972. The other thing I should add to that is the same thing. I'm losing track of what I want to say. That, you know, there's a lot of things that actually. Oh, Friedrich Hayek, right? When he talks in his 1945 paper about how markets can actually spread knowledge, he actually wasn't talking about statistical knowledge, about bits and pieces. He was talking about complexity. And when you read this, he had an intuitive feeling of computational complexity, but it wasn't defined yet. To expect, with the exception of what Alan Turing and also Church were doing. All right.
Looking at this square, I'm thinking that maybe we can define like satisficing through probability, okay?
I don't want to do that. The reason is the space is too big. You cannot, there is not such a thing like an uninformed prior here. Right? So this is like the real numbers on the real line. There is no uninformed prior there. Whatever prior belief that you have, if you're really an expected utility guy, you have to commit, like, you know, Leonard Savage, you have to commit to something that actually will then bias your decisions. So why then not commit to anything? Right? Why insist on probability theory? In fact, Kolmogorov himself, he has a beautiful speech that he gave at the end of his life in Nice in France, about exactly this difference between probability theory, where you use it, and what he called finite mathematics, combinatorics. And he said, please don't use Kolmogorov probability theory for finite mathematics, right? And he used, of course, Kolmogorov complexity as a way to decide, right? All right, there was another question at the back.
Thank you, Peter, for this super fascinating talk. So I think you blew my mind because I was totally unaware of these things. But I was wondering, maybe I missed it. When you present these problems, let's say, to humans, you know, do you tell them if there exists an optimal solution? Because you mentioned different examples, you know, like me going to the supermarket. I see that I may have no clue about what the optimal value is. So I start to play around and, you know, I get experience, I go more often, I build on that and stuff. So, but when I do an exam, I know I can get a 1, you know, or a 6. So I know what the best grade is and the worst grade is, and which makes me also, gives me feedback about my economic performance. And there I might start maybe using different things. So I don't know if you have any thoughts on this, or maybe I'm just totally off.
You have never done a qualifying exam in real analysis at UCLA in mathematics. I can tell you, I did that. And the professor who gave us that, the question said, I don't know whether the question has an answer. So, okay, that's but you're asking about experimental design. In all the cases that we actually have done here, if it's an optimization problem, there exists an optimum. Right? Now, it's interesting to actually do what Hassan has been doing is to tell them what the optimum is. And then tell them how do you get there. It does not simplify the problem. It's still an NP complete problem, because now you have to find the combination of items that get there. It's actually really interesting to do this and see how much effort people have to spend. And then see how markets can actually help people here, and where is most effort spent collectively as a society. This is one of the last points that I made, right? So there's a lot of ramifications of this type of research on topics that humans, these are problems that humans are very good at. Machines are not very good at this, right? So at the AI type of version, except if they recognize this was, you know, I was talking to ChatGPT about this, because I said, you know, okay, you're only allowed to use arithmetic. Here is a problem that I want you to solve. Tell me how you reason. You know what it did? First, it didn't show me the reasoning. And second, it just said, here's my result. And it was a stupid algorithm, right? But then he got the right result. So I asked, well, wait a minute, why did you use this, right? And then he started talking about knapsack problems. He said, I didn't say anything about knapsack problems. So he uses in the background, it knows to recognize problems and then talk to the operations research guys, can you help me solve this problem? Of course, they don't literally talk to operations research guys, but there are standard solvers for this. So the way the AI kind of cheats in this is that it recognizes the problem and then asks standard solvers of doing it. I want AI to actually solve this based only on its language capabilities and the reasoning itself through it. We know that it can't even solve very simple problems like the Tower of Hanoi, only using reasoning, right? So this is all related to what you're saying. I mean, it's fascinating. Actually, what I also, this question came up in Michel's and Hassan's talk. What about learning, right? So if people, we had this one clinical trial where people had to come back 4 times in a row because it was a within-subject clinical trial. You got 4 pink pills. One was placebo, the other one was Ritalin, Adderall, and these are commercial names, right? And then modafinil, right? And you didn't know what you were taking, but you were asked to solve the same problems. Question is, after 4 weeks, are people better? No. Wait a minute, there is a problem there, right? So we have to research this. We're also, you know, what do we do in school? We teach people calculus, we teach people to memorize things, everything that machine learning is much better at. Right? And the stuff that actually we are pretty good at is this type of stuff. And monkeys as well, by the way. Right? Monkeys are remarkably good at this. partially also because maybe the fact that their working memory is better than humans, and this depends on working memory, or the algorithm that you choose may use different working memory depending on what algorithm you choose. This has to do with space complexity. Adam Sanjurjo in Alicante is working on that space complexity for humans, how he can help. So yes, does that get at answering your question?
Good enough.
Good enough, yes. Good, that's important. Any more questions? Got it.
So I'm sort of wondering at behavioral NP completeness. So at least the decision problem version of the knapsack is NP complete. So if we are talking to computer scientists, it's the same as a bunch of other problems. But then you have a lot of data and have recognized empirically a series of regularities of actual human behavior. So I'm wondering, if we do that and start translating those problems within the NP complete class, is the behavior of humans actually reacting to that? Is there ways to reformulate a problem such that we are better, or are we doing the same things in equivalent problems?
Okay, so we studied once how people do on traveling salesperson versus the other ones, and you see correlation. So if you're good at one of them, there's some correlation with the others. But this was only a preliminary study. It wasn't meant to actually look at that, but yes, there is correlation. And that the theory predicts that this should happen. What does happen, of course, if I give you a 3-set problem, we have a visual representation of that. That is not a problem that most people actually encounter in everyday life, so it's hard for them to get into it. Michelle has worked on Sudoku puzzles, and most of her participants have never seen Sudoku. So it takes a while for them to actually realize what's going on there, whereas a traveling salesperson problem or a weighted cost shortest path problem, everybody realizes that. If you somebody has had to go from here to the beach, right? With congestion, which is a difficult problem when it's congestion, but so I think there are framing effects. And I should admit, we were not the first to look at how people solve these problems. It was the Journal of Problem Solving, now defunct, right? They did what Herbert Simon told them to do, is just ask people what they're thinking. And it ended up with not very much because they didn't have the structure of these problems. And then as a result, they were emphasized a lot. For instance, traveling salesperson problem, how you actually have to present it to make it easy for people. But then you mess with the difficulty of the instances, so it wasn't clean enough. Right? And so we revived this whole research by looking at humans, thanks to computer science, right? Theoretical, and this phase transition is a big thing, right? So markets actually put themselves right in the phase transition. Right? It's absolutely amazing. You set up an experiment a la Vernon Smith, right, where you expect the prices to drop to 0. They actually move the budget problem right in that region. It's fascinating to see. It's reverse gravity. Yes.
Thank you.
So yeah, a good question. But we have started. We have a good foundation to start looking at these problems. And of course, policy implications for, please don't always use markets to solve people's problems, right? Because it may make people's lives difficult. But, I only do the fundamental research on that. Michelle worked on credit cards, complexity of credit cards. And that is, it's crazy there, right? So you should talk to her about the results.
Thank you. Any other questions? You're not. Thank you very much for an excellent talk.
So, thank you. I have something to tell you now. So, as you know, tomorrow we have the gala dinner and we have a transfer at 7:45. Tonight, yeah, not tomorrow, no. Tonight, 11:45 in front of the Hotel Luz, okay? For coming back, I tried my best to have a bus at 11 o'clock. I was said that this is gonna work, but 10 minutes ago they told me this is not gonna work. So we'll have 2 buses at 11:30 and the last one at 12, okay? And that's all. Enjoy the rest of the conference. Thank you.